Hi students, welcome back to another lecture series where we continue with our enzymology lessons. Now, if you have attended the last lecture, we discussed regarding factors that affect enzyme activity, and to recap that, we will show the slide. First, we discussed about temperature, few enzymes that that act in an optimal condition in a temperature, and the temperature is to their activity curve looks like this. It's a bell-shaped curve. It means the enzyme activity rises with rising temperature, and then ultimately when the temperature rises further, the activity will fall off. So that narrow range, this is the range where the enzyme activity is maximum. It's known as the optimal temperature range, and this will come as an explain why type of question, and then you need to draw this curve. And the same question may come irrespective of the factors. It may come with respect to temperature, it may come with respect to pH, it may come with respect to substrate concentration. So just go through your textbook and enzyme concentration. So all of them have got similar bell-shaped activity. The activity increases to a certain point and then it's maximum and then it falls off, right? So this is it. Now in today's lecture we will continue with Michaelis Menten Equation and kinetics, or Michaelis Menten kinetics. This is one of the most vital areas of enzymology, and that will help you to understand the important long question, that is enzyme inhibition, right? Because enzyme inhibition will be one of the most favorite topic that will be asked in Viva as well as in theory question. So this Michaelis Menten equation, what does it say? It tells us the relation between substrate concentration and the reaction velocity. Now this reaction should be by heart by everybody. You shouldn't make a mistake in writing this equation. It may seem very easy when you are looking at the slide, when you are reading from the book, but trust me, if you don't write this equation on your own, even this simple equation may appear pretty messed up during writing answer script. So it's V0. So left is V0. So it starts from 0. V0 equals to V max multiplied by S divided by Km plus S. Km being the Michaelis Menten constant. Now the common confusion that happens is between numerator and denominator. Students often write V max over here. So please, it's my request, just remember, at least remember this equation. Because even if you fail to answer, or even if you cannot answer any question, maybe due to stress or anything unpredictable situation, even if you fail to answer any enzymology question, this is the question that will make you pass. Examiner will ask you at the last that please tell me Michaelis Menten equation. At least tell me that thing. If you write that thing correctly and if you explain this is the initial velocity, this is the maximum velocity, this is the substrate concentration, and this is the Michaelis Menten constant, at least this will give you the credibility to pass the exam, right? So these are the various abbreviations that we have been using in the Michaelis Menten equation. Now the next step of this equation is drawing of the curve, how the Michaelis Menten curve actually looks like. So the curve is actually very easy. This, when it starts from 0, the reaction velocity is 0, so this is V0, right? This thing is given in every textbook, and again I am telling you, this is a revision class, you have already done this, so I hope you are acquainted with this. So the time, after some point of time when the velocity cannot increase further, we call it Vmax, right? So it's the maximum velocity. Now there will be a point when it is simply half. So suppose this is 4, if we are just putting it in a log scale, okay, in a graph paper, suppose this is 4 unit, so we need to calculate the half, okay, so this is 2, so this is Vmax by 2. Now in the latest curriculum you don't need to derive all this. Previously, in previous year's question or even in Viva, you may have been asked, please derive the Michaelis Menten equation, or tell me how the mechanism, or tell me how you can derive the value of Km, etc. But in this year, you just need to know the reaction. Yes, it is very difficult conceptually. It is very easy if you know the mathematical formula. You can go through your textbook. Your textbooks still have those, but it will not be asked this year, right? So it is better to only focus on those which will be asked and utilize the rest of the time in studying anatomy or something else. Anyway, so this is Vmax. Now, the abscissa and ordinate, meaning the x-axis and y-axis, the x-axis being the substrate concentration and the y-axis being the velocity. So, over here, whatever plot intercepts we are doing, this is the substrate concentration. So, if we drop an intercept from the Vmax by 2, that is half Vmax, the substrate concentration that we get here is the mathematical value of the Michaelis Menten constant, right? How you need to derive it? It's pretty easy. You can go and see your textbook, but for the sake of this curriculum, this will not be discussed today. Anyway, so there are some assumptions. Now, this is very important for Viva, extremely important. What are the assumptions or prerequisites for Michaelis Menten equation to be true? So, there are 3 prerequisites or 3 assumptions. So, what are they? This, right? So, number 1, the substrate concentration is much higher than the enzyme concentration. This is the absolute important. This you need to remember. For the Michaelis Menten equation to hold true, we assume that the substrate amount is so enormous that enzyme is always occupied. There is nothing called free enzyme. So, concentration of substrate is much higher than that of enzyme. It is infinite compared to the enzyme concentration. So, this is assumption number 1, right? Number 2 and number 3 are more or less related. Depending on your textbook, you may not find this number 2 or you may not find this number 3. But if you want to score more marks, it is better to increase the number of points. Okay, don't write relevant point. The substrate concentration is very higher, the enzyme concentration is much lower, the substrate concentration is higher than enzyme concentration. So, don't write one thing in 3 different points, okay? You should be relevant, you get my point. So, the initial reaction velocity is considered, means we do consider, see, this is the Michaelis Menten plot, right? Now, generally, we don't consider when the velocity of the reaction is approaching the peak. Yes, we consider a point that is Vmax, but most of the calculations of this equilibrium or equation occurs in this area when the reaction has already started. Why? Because the point here actually behaves like a straight line. A little bit later it becomes a parabola. So, it is the initial phases when the Michaelis Menten equation holds true, right? So, you can see already see there are many flaws in here, right? But still, back in the day, both of them got Nobel Prizes because this thing was actually able to solve many problems related to enzymology. And lastly, steady state hypothesis is followed. So, what is steady state? This will be another Viva question. So, steady state means, you know what happens, enzyme plus substrate reversibly forms enzyme substrate complex, and from that it becomes enzyme plus product, right? Steady state hypothesis states that, okay, the rate of formation of this equals to the rate of breakdown of this. It means the rate at which enzyme substrate complex is formed is same as the rate at which it is broken. So, it means what? See this arrow. So, what reaction is leading to formation? It means this. So, enzyme plus substrate is forming the enzyme substrate complex. So, this arrow is the forward reaction, right? And enzyme substrate complex is getting depleted by 2 ways. Number 1, in the reversible reaction, it is again becoming enzyme and substrate, and in the forward reaction, it is becoming enzyme and product. So, this rate of formation of enzyme and substrate is equal to rate of formation of product plus rate of reversing into enzyme and substrate. Am I clear? Now, there is a state when this equilibrium is not reached, means rate of formation of enzyme substrate is more than product formation. This is known as pre-steady state kinetics. Naturally, when the steady state kinetics has not been reached yet, it is known as pre-steady state. But for first year students, you don't need to know about pre-steady state kinetics, or at least you need to know what it is, maximum, not more. Exception to this Michaelis Menten constant or Michaelis Menten equation is allosteric enzymes. Now I think you can hear the sound of hammering because there is some hardware construction work going on in the area. Anyway, you just focus on what I am saying. So question will be asked, why allosteric enzymes do not follow Michaelis Menten equation, or how allosteric enzymes are exceptions. So this is another explain why type of question, right? So whatever points I am discussing now, you need to write, and if this comes as a explain why type of question, you need to write exactly these points. So number one, very important, in case of normal enzyme, I mean non-allosteric enzyme, we read that there is a site that is known as active site where the substrate will bind. Now the model of active site could be rigid depending on lock and key model, or it could have been compliant based on the Kostland's induced fit model. So active site is the site where substrate will come and bind, and then product formation will happen. In case of allosteric enzyme, and that active site is single in case of normal enzymes, allosteric enzymes have got multiple active sites, and this leads to the phenomena of cooperativity. It means binding of substrate to one active site increases the activity of enzyme. So enzyme activity is not directly dependent on substrate concentration. The equation is not linear. In case of Michaelis Menten equation, the reaction should be linear. At some point of time it goes and forms a parabola, that is true. But in case of allosteric enzymes, if you consider the reaction, it becomes sigmoid or S-shaped. Very important. Also the same phenomenon of cooperativity you have already studied in case of hemoglobin, right? In case of hemoglobin, binding of one oxygen facilitates binding of more molecules of oxygen till all the 4 oxygen binding capacity are saturated. So this is point number 1. Multiple active site, that leads to the property of cooperativity, and that leads to sigmoid curve. You need to mention all these 3, right? So this is point number 1. Why allosteric enzymes cannot follow Michaelis Menten kinetics. Number 2, allosteric enzymes are influenced by substrate concentration. Now this might seem very vague. What do I mean by it? See, normal enzymes are also influenced by substrate concentration, but allosteric enzymes, depending on the substrate concentration, undergo something that is known as conformational change. So allosteric enzymes remains in 2 conformation. One is T or tight or taut conformation, T-A-U-T, okay, and one is in relaxed conformation or R. Excuse me. If the substrate concentration is lower, the enzyme remains in the T form, and if the substrate concentration is higher, the enzyme remains in R form. So the enzyme that changes its conformation according to the substrate concentration cannot follow Michaelis Menten kinetics, because in Michaelis Menten equation the enzyme activity should remain constant with respect to substrate concentration. Okay, so this is number 2 hypothesis. Conformational change of enzyme is not allowed in case of Michaelis Menten equation. And lastly, allosteric enzymes are regulated by other molecules as well. For example, 2,3-BPG. There are multiple allosteric enzymes in glycolysis, Krebs cycle. You have already read about that, right? And you have already read how 2,3-BPG can influence the role of glycolysis. So allosteric enzymes have got sites that are other than active sites, multiple active sites. Also, they can be regulated by something other than substrate. So if we are only calculating substrate concentration, Vmax, etc., the whole ball game will change whenever 2,3-BPG or any such factors that affect their enzyme activity or allosteric modifiers, they will completely change the equation or the curve. So these are the 3 reasons why Michaelis Menten equation cannot be followed by allosteric enzymes. Very important conceptual question. I don't know it has been discussed or not, but do remember now. So we move on to the Km, the value of Km, I already told you from the graph, it is the substrate concentration at which the reaction velocity is half the maximum reaction velocity. Okay, it is a substrate concentration at which velocity is half Vmax. Fine. So you can simply replace in the Michaelis Menten equation, you can replace the V0 by Vmax by 2 and you will get Km equal to S. Simple, mathematics is very easy over there. Now this definition is a must know area. Along with the Michaelis Menten equation, the definition and the importance of Km is also must know area, by which what I mean, not knowing this will make you fail in exam. You must know this, right? So what is the significance of Km? Number one, it's a unique property of enzyme. Every enzyme has got a different Km depending on the substrate. Okay, it's substrate specific. And more importantly, it indicates the affinity. Now the affinity and the value of Km is inversely related, right? This you already know by now. So an enzyme with low Km will have higher affinity towards that substrate, and an enzyme with high Km will have low affinity for a substrate. For example, a very easy, most common example that you need to remember is glucokinase has got a very high Km for glucose, glucokinase, and hexokinase has got a very high Km, has got a very high affinity and a low Km, right? And this question, we are not discussing carbohydrate metabolism over here, so when we meet in person we will be discussing this. Why? What is the reason? Why blood glucose regulation? Why in blood glucose regulation this value or this role of hexokinase and glucokinase and their Km has got such an important role? How liver acts as storehouse of glucose? Why hexokinase acts in periphery and glucokinase only acts in liver? So these are all pieces of puzzle that are answered by this value of Km, and for that the concept of enzymology needs to be very clear. But just for this short note, or if you are asked about Km, just remember high Km glucokinase, low Km hexokinase. Conversely, it means hexokinase has got high affinity for glucose and glucokinase has got very low affinity for glucose. Now if you know the answer to this question, when I post the video you can answer that in the comment section. I will follow up whoever is answering it correctly. Next, we deal with another Viva short question or a short note or a one-liner, that is turnover number. Remember, a long question doesn't mean you need to write pages after pages. A long question means nowadays multiple short questions that are clubbed together to form one 15 marks question. So all of this, turnover number, what is Km, everything may be there in a single question itself. So what is turnover number? Turnover number is also very easy to understand. We are converting, basically it's the activity of an enzyme or the number with which we can understand the activity of an enzyme. Now what is the role of the enzyme? The role of the enzyme is to convert substrate to a product, right? And in what time it is converting a substrate into a product? So per unit time, okay? So the number of substrate molecules converted to a product in a unit time by one single molecule of enzyme when it is fully saturated. Very important, fully saturated. We are considering Michaelis Menten kinetics. So fully saturated means substrate concentration is much higher than the enzyme concentration. Dakar, post lunch session में ऐसे ही होगा. So excuse me, right? So under standard condition, now this is your homework. What do you mean by standard condition? There are standard condition, biological standard, and there is alchemical standard. Okay, in biological standard, temperature, that atmospheric pressure remains the one, okay, but the temperature is different. For when you are discussing physics and chemistry, it's absolute zero, right? And when you are discussing enzymology, the standard condition is what you will answer me in the WhatsApp group. Not right now, just see this video. So under standard conditions, Vmax is actually the turnover number. Naturally, when the enzyme is fully saturated, it is at its maximum ability. So during that time, single molecule of enzyme, suppose we will convert 80 molecule of substrate to the product. So we tell that the turnover number of that enzyme is that thing X. Now, naturally, enzymes with higher turnover number are more efficient. Naturally, the thing that will do more activity is much more efficient, right? Now, there is one more assignment. What is the unit of turnover number? Okay, or what is the unit of enzyme activity? There are two units. Number one is cattle, okay, and number one is international unit, IU. So note down the homeworks I am giving you. I'll be asking them next day, or if you have got the willingness, you can post it in the WhatsApp group. So I want you to answer the relationship between cattle and international unit. Just research when the class is over. So first tell me which unit is bigger, okay, and then you write the relation or the formula by which we can convert one cattle to one international unit. So this is very important, but know this, turnover number of an enzyme is the unit of its efficiency. Next, from the Michaelis Menten plot, we come to our main area of interest, that is Lineweaver Burk plot. Now, the Lineweaver Burk plot is simply derived by just inverting or reciprocating the equation, or 1 divided by that. So, if we divide both the right side and left side of the Michaelis Menten equation, or if we invert, after final simplification we will get what is known as Lineweaver Burk plot. So, it is simply reciprocal. Since we are reciprocating both the left and right side and both the numerator and denominator, this is known as double reciprocal plot. Most importantly, or more importantly, why the double reciprocal plot is important for undergraduates or for all enzymologists for that matter? Because it converts the parabolic curve. It converts the parabolic curve of Michaelis Menten equation to a more straight line. So this is very important. It converts this into this. Now, what's the advantages? Advantage being the intercepts are very easy to determine. The x-intercept gives the Km and the y-intercept gives the Vmax. So, determination of Km and Vmax is accurate. Over here, we need to draw tangents and then we need to calculate. Drawing the half Km value is fine, but when we add inhibitors, the equation becomes much more complex. Whereas in straight line, any straight line is a 2-degree equation, okay? This is quadratic formula and this is y equal to mx plus c. Anyway, I am not going into maths, it will blow your mind. So, explanation of different type of enzyme inhibition is easier to understand, and x and y intercepts gives us a much more accurate and easy way to determine the value of Michaelis Menten equation or Michaelis constant and the Vmax of that enzyme. So, Km and Vmax determination is easier and enzyme inhibition studies are easier. So, it makes the job easy. So, these are the advantages of double reciprocal plot. Now, slowly we will be going into a territory. As I told you, this year the derivation of the equations are omitted, right? So, understanding enzyme inhibition, which was laborious but easy previously, will be now in a short form, but it will be difficult to understand because you just need to ratify. I mean, you just need to by heart them, but that will get your job done. You will be not asked to derive the equation, right? So, when we come to enzyme inhibition, based on the how much time is left today, fine. Based on the enzyme inhibition, these are the areas that we need to focus. So, what are those? What are the different types of enzyme inhibition, right? You need to know about competitive enzyme inhibition. What are the kinetic changes? It means you need to know both how it affects the Km and Vmax, how it affects the Michaelis Menten curve, and how it affects the Lineweaver Burk plot. But you will be asked to draw, illustrate with double reciprocal plot. Remember, you can know Michaelis Menten equation, especially the ones who are the CAs will be hunting you big time, and the good students too. But everybody is expected to draw the double reciprocal plot. Okay, Michaelis Menten plot should be known. It's not a must know, but Lineweaver Burk plot is a must know area. So likewise, you need to know both competitive and non-competitive curve, how it affects Michaelis Menten equation. You need to know what are the irreversible equation or irreversible in enzyme inhibition, and lastly suicidal inhibition with example. Now among them the most important is competitive. Okay, and occasionally you may get a comparison between competitive and non-competitive, how the curve looks like, how is it different. So let's study them one by one. First, the basic concept, what are the types of enzyme inhibition. Now this is one area where most students make mistakes, because in your textbook it's only given competitive and non-competitive, right? But if you just keep on studying higher or better textbook, you will find something called uncompetitive. Then the students get confused between reversible and irreversible. Remember, and don't make this mistake ever again, whatever you are reading, competitive, non-competitive and uncompetitive, all of them belong to reversible type of inhibition. This is extremely important concept. And irreversible inhibition is something else totally. We cannot tell that competitive is reversible, non-competitive is irreversible. This is the most common mistake that students tend to make unless they are guided properly, right? So I hope you and your batch will not make this mistake ever again. Competitive, non-competitive, uncompetitive, all three belong to the reversible category. Fine. So now let us, so wherever you are now telling competitive, it is what? It is reversible competitive inhibition. There is nothing called irreversible. Okay, I am just emphasizing on this because it belongs to a reversible category. So now let us know what are the must know areas that will help you pass the exam by knowing competitive inhibition. This is the bare minimum that you need to know about competitive inhibition. You don't need to read pages after pages from your textbook. So here it goes. Number one, the most important point that you need to know, or that you already know by now, that the inhibitor looks like the substrate. So inhibitor is a structural analog of the substrate. Therefore, both of them will compete with each other in order to bind at the active site. So it is very easy to, why? See, both of them are the structural analog. It looks like the substrate, but it is not exactly the substrate. It is an inhibitor, it is different. So based on the active site, the structure of both of them can well fit into the active site, right? Now since both of them are competing with the single site, there may be two outcomes. Number one, enzyme and substrate can form the enzyme substrate complex, and then they can form enzyme and product, just like what used to happen normally. Or the enzyme inhibitor will combine with the enzyme. It will have a different Ki. Ki means Michaelis constant of the inhibitor. Remember, Michaelis constant is substrate specific, right? So Ki will be acting over there. This is the equilibrium constant, and this will now become Ei. So one enzyme and inhibitor forms a complex. There will be no formation of product. But the good thing over here is, since they are competing with each other, if we are increasing the concentration of substrate so much, remember in any equilibrium reaction, if we increase the one side, the reaction will be driven to the other side. So if the substrate concentration is increasing so much that it overwhelms the concentration of the inhibitor, the reaction will go towards this and inhibition will be reversed. So this is competitive inhibition and this is the reversible one. So by increasing the substrate concentration, inhibition can be reversed. Remember, although I have told you the competitive, non-competitive and uncompetitive all belong to reversible, you don't need to know the mechanism of reversal in case of non and uncompetitive. Okay, that will not be asked. That is in postgraduate syllabus. So I welcome you, whoever has got the perseverance and has got the desire to pursue a career in research. If anybody cracks MD biochemistry or genetics for that matter, then I will be teaching you personally how competitive, non-competitive and uncompetitive reversible inhibition occurs. It's there in Leninger. You can go and study, but it's an utter waste of time now. So this is the thing that you need to know for competitive inhibition. Now we need to study the kinetics. So number one, I have told you it looks like substrate, it competes for the same active site, substrate concentration can increase to reverse the enzyme inhibition, right? Now this is this is how it affects the curves. Remember, it's my earnest request to you that please draw this curve on your own. Otherwise, it will be very confusing and you will always mess up between the competitive and non-competitive, right? So first thing, what happens in competitive? Vmax remains unchanged, right? If you see the reaction, how competitive inhibition happens, this is very easy to derive, but for now there is no question of derivation. Just remember, Km is increased. By increase in Km, we mean the affinity is lowered because Km is inversely proportional to affinity. So affinity of the enzyme for the substrate is lowered in presence of a competitive enzyme inhibitor. Again I am repeating the sentence, you can write it down. Affinity of the enzyme towards the substrate is lowered in presence of a competitive enzyme inhibitor, right? So what happens? Since Vmax remains the same, right? So ultimately both will attain this maximum velocity, but normally what will happen, the reaction velocity will be increased very much and then slowly it will reach towards the peak. However, in case of inhibitor, with inhibitor what happens, the reaction velocity is low to start with, but as we are increasing the substrate concentration, right, the thing will be reversed and then ultimately it will attain the maximum velocity, right? So this is the basic concept. Now this thing, okay, you may not know, you may choose to forget this, but this is what you should absolutely remember. You may not know the value of the slope, okay, this mathematical calculation is not a must know area, but this is very important. The Vmax remains the same, so y-intercept is the same, right? This is actually minus 1 by Km, so this is a negative, right? So if Km value is increased, minus 1 by Km should decrease. So with inhibitor present, the x-intercept actually happens over here. Students often confuse between this blue and red line. They make this one with inhibitor and this one without inhibitor. Just go through your textbook or just note this slide or just whatever is your reading sources, just practice this diagram over and over again. Okay, it's my request to you. If you want to score good marks, you need to practice both the diagrams. But remember, the Vmax is unchanged, Km is increased, that is affinity is lowered, and this is the Lineweaver Burk plot. Remember, this will come as a long question. If one question is asked in enzymology, it will be enzyme inhibition. I am already telling you repeatedly. So next are the examples. So see, you can, if you are asked in Viva, what are the examples, you can get away with it by saying one or two examples. So number one, malonic acid is a competitive inhibitor of succinate dehydrogenase or malonate, right? However, I have listed many examples. Why? Because each of them has appeared as an MCQ in some or the other colleges. How they are given? One example, there are multiple substrates or multiple inhibitors are inhibiting multiple enzymes. So 4 examples will be given. So either they may be given as which one of them is a competitive inhibition, then you need to choose between the wrong one and the correct one, or they can be given in all except. So all 3, maybe 3 of them will come from here and 1 they will give some non-competitive or uncompetitive example, and then you need to select the odd one out. So remember, I am reading it once again. Malonic acid is a competitive inhibitor of succinate dehydrogenase. PABA, para amino benzoic acid, okay, that is an inhibitor of the enzyme dihydropteroate synthetase. all this will come, or all this is already included in your syllabus and you don't know it yet, right? Methotrexate acts as an anti-cancer drug, trimethoprim acts as antibacterial drug, pyrimethamine acts as anti-malarial drug, and warfarin or dicumarol acts as anticoagulant. So all of them are example of competitive enzyme inhibition. All right. So if you are asked about competitive inhibition, these are the things that you need to know. Substrate analog, active site, substrate concentration increase, enzyme inhibition reversed, Km increased, Vmax unchanged, and these are the one or two example of competitive enzyme. Next, we go to non-competitive inhibition. Now, what is the difference between competitive and non-competitive? Number one difference is the inhibitor has no structural resemblance to the substrate. Alright, the inhibitor and the substrate are completely different. However, and in the previous one, the competitive, the inhibitor and the substrate was binding to the active site, right? Non-competitive inhibition, in non-competitive, the inhibitor binds to a site other than the active site. By binding in a site that is other than the active site or different to the active site, it induces a conformational change in the enzyme and the enzyme will cease to function, right? Substrate binding occurs, definitely the enzyme will bind to the substrate, but the product formation will be decreased, okay, catalytic activity will be lowered. So this is what is happening in case of enzyme or non-competitive inhibition. See, normally what happens, enzyme and substrate is binding to form enzyme substrate complex and then it forms the product, right? Now, this inhibitor can either bind to the enzyme substrate complex, right, or it can bind to the enzyme at a site that is other than the active site, and then it will lead to the formation of a thing or a complex that has got both enzyme and substrate and inhibitor. So this will ultimately lead to lowering of the formation of enzyme substrate complex, because some amount of ES or some amount of E is already involved in formation of ESI. So product formation will be lowered. This is the diagrammatical representation. See, enzyme inhibitor is binding at a site that is other than the active site. This one is the active site and this one is the site for binding of the inhibitor. Both have bound and ultimately ESI formation has taken place. Fine. So this is the basic molecular mechanism of non-competitive inhibition. And inhibitor does not look like substrate, it binds to a site that is other than the active site, and after binding it induces a conformational change that leads to decreased catalysis or decreased product formation, right? Important, by increasing the substrate concentration, inhibition cannot be reversed. Very important, this can be reversed, but not by increasing the substrate concentration, okay. This thing is given in your textbook and this is here, most of the students make this mistake, they take it as irreversible. No, we are talking about reversibility by increasing substrate concentration. Reversibility can be done by many ways, alright. Substrate concentration increasing is only one aspect of that. If you consider that aspect only, that will not work in case of non-competitive. But non-competitive, this type of ESI, you can see this is a reversible arrow, everything is actually reversible. So non-competitive inhibition is a type of reversible inhibition that cannot be reversed by increasing substrate concentration. So this concept should be absolutely clear. So if you are asked to write a difference between competitive and non-competitive, so you already have 4 points. Number one, not structural analog, inhibitor is not structural analog. Over there it was binding to the active site, here it does not bind to the active site. Over there it could have been reversed by increasing the substrate concentration. In case of non-competitive, it cannot be reversed by increasing the substrate concentration. Next difference is between the kinetics or the changes in Km and Vmax. In case of competitive, the Vmax was remaining unchanged and the Km was increasing. Over here just the reverse thing happens, right? Vmax is decreased and Km remains unchanged. That is the affinity of the enzyme towards the substrate. It remains same. Why it remains same? Because the active site will be only occupied by the substrate only. I have told only twice, right? The active site will be occupied by the substrate because an inhibitor is not competing for the active site. So there will be no change in affinity, but ultimately the conformational change will lead to decrease in enzyme activity. So in case of, you already remember, in case of competitive, the inhibition curve looked like this. Ultimately it was reaching the same Vmax, but over here this is Vmax and this is the new apparent Vmax, or whatever you can call it, Vmax dash, or you can call it Km dash, or you can call it Vi, that is Vmax with inhibitor, anything that you need to say. The value of Vmax will decrease. However, the value of Km will remain unchanged. So Vmax by 2 will have the same intercept. If we look at the Michaelis Menten curve, it is much easier to denote in case of Lineweaver Burk plot. You can see the x-intercept, that is the minus 1 by Km, is the same. However, the Vmax is decreasing. So here how the Lineweaver Burk plot looks like. So again I am telling you repeatedly, it's my earnest request, please practice these two figures, the competitive enzyme inhibition and the non-competitive enzyme inhibition Lineweaver Burk plot, and also the Michaelis Menten plot if you want to score good marks on your own. So three things that you must know: the Michaelis Menten equation and the definition of Michaelis Menten constant or Km, and these things, the Lineweaver Burk plot of competitive and non-competitive inhibition. Now in your textbook you will only find example of competitive and non-competitive inhibitions. You will not find easily, or even if you find, it may be wrong. That is the example of non-competitive inhibition. This is the example that is the most correct for undergraduate students. So alanine is the non-competitive inhibitor of pyruvate kinase. Very important. Pyruvate kinase does what? Okay, phosphoenol pyruvate to pyruvate. So phosphoenol pyruvate to pyruvate in case of glycolysis, and then it undergoes transamination, transaminase to form alanine. This alanine, and over here is PK, pyruvate kinase. This alanine is a non-competitive inhibitor of pyruvate kinase. Very, very, very important. Alanine non-competitive inhibitor of pyruvate kinase. If examiner asks you, fine, can you tell me some other example? It means at that point you have impressed the examiner so much that you have already crossed the honors marks territory and he or she is expecting a real good answer from you. Then only you will be uttering the name of this CYP2C9. It is a enzyme or inducible enzyme, or that is, it is one of the cytochrome P450 group of enzyme. I think you have been taught xenobiotics class, cytochrome P450. So all cytochrome P450 inducers and inhibitors are example of non-competitive. So I will tell you one example, that is phenyl isothiocyanate, PITC. Phenyl isothiocyanate non-competitively inhibits CYP2C9. Okay, it's difficult. At your level, just remember pyruvate kinase is a non-competitive inhibitor of alanine. If asked, then you can say CYP2C9 inhibitors are all non-competitive. 8 minutes left. I think I can go into uncompetitive because those things are not included in much details. So remember, if you are asked about competitive and non-competitive inhibition difference, whether in theory or in viva, you must include the changes or the reaction, basic reaction, how the substrate competes or not competes, how it can be reversed or not reversed by increasing substrate concentration, mention the changes in Km and Vmax, mention the figure, and also give examples. Alright. Next, we look at reversible uncompetitive inhibition. If you are studying Leninger or other textbook, Over there, competitive and uncompetitive are the two main categories, and non-competitive comes much later. This is important. Why? Because the inhibitor only binds to the enzyme substrate complex. Mind it, in case of non-competitive, it could have bound to both enzyme or ES, and ultimately enzyme substrate ESI complex was formed. But in case of uncompetitive, inhibitor can only bind to enzyme substrate complex, right? So only after the ES has formed, it can form ESI. The mechanism is the same. It does not look like substrate. Only category where inhibitor is substrate analog or structurally similar is competitive. So in all the other two, the inhibitor does not look like substrate. But how does it differ from non-competitive? In non-competitive, even I could have bound to this. EI plus S was leading to formation of ESI. This is not happening in case of uncompetitive. So in case of uncompetitive, inhibitor is only binding once the substrate has bound to the enzyme, and this also cannot be reversed by increasing the substrate concentration. So by increasing the substrate concentration, inhibition cannot be reversed. And how it differs from both competitive and uncompetitive? In this case, the Km and Vmax are both decreased. Okay? So how? Can you tell me how the Michaelis Menten curve will look like and how the Lineweaver Burk plot will look like? In case of competitive, it was looking like this. It was starting low, but ultimately it was reaching. In case of non-competitive, it was starting like this, but it was remaining like this. In case of uncompetitive, what will happen? Both will decrease. So it will start low, the slope will be low, and it will not reach at all. Okay, so if we compare compared to this, if you draw uncompetitive, it will start like this and ultimately it will stop here. So both the slope, the increase in the activity, that is the Vmax, will be decreased, and the Km will also be decreased. And if we look at the Lineweaver Burk plot, how it will look like? It essentially looks like parallel, where both Km and Vmax both are decreased. Okay, trust me, you will not be asked about the changes or graphical representation of uncompetitive. You may not be asked about uncompetitive even if you don't answer that well. But for the good students, this is a nice to know area, right? And as I have shown in the slide, inhibition of NMDA receptors in the brain, N-methyl deaspartate. Remember, inhibition of NMDA receptor is one of the mechanism of ammonia toxicity. Glutamate plays a role. So inhibition of NMDA receptors in the brain is an example of an uncompetitive inhibition. Now, this inhibition of NMDA receptors, there are multiple types of inhibition. So part of that NMDA receptor inhibition is done by uncompetitive mechanism. So competitive, uncompetitive and non-competitive. Remember the changes in Km and Vmax, and remember the Lineweaver Burk plot in case of competitive and non-competitive. So I think that's it for today. In the next class, we will be going into irreversible inhibition, and also we will be discussing what are the mechanisms of by how we can regulate the enzyme activity. So stay tuned for that. Feel free to get back to me with your queries in the comment section. I will see you in the next class. Till then, bye and take care.